Greetings everyone and welcome back to part 2 of Stellar Evolution for National Science Week 2021. Of course, I'm talking to all the good folk who tuned in last week from the Wangaratta Public Library. Welcome back. So tonight we are going to finish off the rest of this talk, and we're going to talk about supernovae. We're also going to talk about the end product after a self-destruction of a high mass star. We'll talk about neutron stars, pulsars, and of course those enigmatic black holes. But just to recap what we discussed last week, and of course you can catch the full replay on the Gravity Discovery Center and Observatory's YouTube channel. But we basically covered how stars are born, what are stars, how big they are, how hot they get, different colors, different temperatures, sizes, etc. We also covered a very important tool used by astronomers and astrophysicists called the Hertzsprung-Russell diagram, which you can use to plot the future evolution of stars such as our sun, which is what we did last week. So what we're going to do now is just briefly cover over high mass stars and how they end their lives in a very spectacular fashion as complete contrast to the very weak bloating and puffing out of low mass stars like our sun. So without further ado, let's crack on with it. So I'll just change screen. Here we are. Oh, we're going to jump straight into supernovae. Perfect. So as we discussed last time, where we had low mass stars that tend to puff out, form a planetary nebulae. The outer layers of the star puff out into the Milky Way or into whatever respective galaxy they happen to live in. What remains is a white dwarf star, and eventually that white dwarf star will cool down. Now, in a white dwarf star, there is no more thermonuclear reactions going on. It is just pure radiant heat. So eventually a white dwarf star will fade off down or cool down into a black dwarf stellar remnant. And I think I mentioned last time that astronomers know for great certainty that there are currently, at this point in the universe, there are no black dwarf stellar remnants anywhere in the entire universe. So that's a pretty cool little bit of knowledge. But let's crack on with supernovae. So we're now dealing with stars that are in excess of 8 times the mass of our sun. And of course, I think I mentioned last time that the thing that determines the size of a star, the temperature of the star, and of course its lifespan is the star's mass. Now, anything over 8 times the mass of our star, that is where or 8 solar masses, that is where you will get a star that will explode. It will go supernovae, or turn into a supernova rather. So let's have a look at this. Now, I showed you a chart last time where we actually had, I'll see if I can get rid of that little square wherever it's gone to. Here we go. Ta-da! Just get rid of that. That's perfect. Okay, so we can see here we have these various burning shells where we have nuclear fusion going on. Fusion, of course, is the slamming together of atoms to create or to synthesize heavier and heavier elements. So, of course, in the outer shell, of course, we've got the hydrogen burning shell where you have hydrogen slamming together to form helium. Okay, that's the next layer down. Helium then fuses together to form carbon. Carbon gets squeezed together, fuses together to form neon. Neon to oxygen. Oxygen to silicon. Silicon to iron and nickel. Now remember, I also told you last week, nuclear fusion stops at iron. Iron, so elements lighter than iron release energy through nuclear fusion, and elements heavier than iron, stuff like uranium and all that other stuff, release energy through nuclear fission, the loss of neutrons, the loss of mass, the splitting of the atom. So iron has the lowest mass per nucleon and cannot release energy through fission or fusion. So it is this dead lump. And that is a problem because you have to remember that a star is in a state of hydrostatic equilibrium. It means that you have pressures from the nuclear reactions forcing the star out, but then you also have gravity trying to collapse the star in. Now, with the increase of the size of the inert iron and nickel core, that outward pressure starts to deplete, because iron is if it tries to, there's too much of it, it's an energy robbing source. It doesn't produce energy, it actually robs energy. So it depletes that outward pressure. And when that happens, when it reaches a critical mass, there is not enough pressure to hold the star up. So the core collapses in upon itself. And as it does so, it collapses down at such a fast rate. Imagine something about the size of Earth, which is about 12,000 kilometers across, suddenly collapsing down to a ball about 50 kilometers across at a quarter of the speed of light. We're talking speeds of around 75,000 kilometers a second, just collapsing it down. Now, of course, when it reaches this very, very, very internal, or this dense state, it cannot be compressed anymore, and it bounces off itself. This is called a rebound. Now, this rebound sends this shockwave in the reverse direction. So instead of going into the star, it now bounces back out, similar to the way that when you drop a basketball onto the ground, the basketball gets compressed to a point where it cannot be compressed anymore, and then it bounces back straight up. So the inner core of the star collapses down, compresses to a point where it cannot be compressed anymore, and then the shockwave then bounces back out. And because a star is sensitive to any internal changes, the external part of the star comes rushing in. As it comes rushing in, it gets met head-on with this ever-expanding shockwave. Now, the shockwave does stall for a period of time, and pressure does build up through various other pressures, such as neutrino pressure and what have you. We won't go too much into that. But nevertheless, the shockwave then starts up again, but it's during that time you do get other elements being produced, but not in abundant quantities. This is where astrophysicists found a certain shortfall of heavy metals, such as platinum, selenium, uranium, gold, during the destruction of a star. And they thought, well, where does this material actually come from? And that was actually found out in, confirmed, I should say, in 2017, the 17th of August 2017, with the merging of two neutron stars, which I'll tell you about neutron stars in just a moment. So nevertheless, the star essentially rips itself apart, and you get what's called a type 2, or a core collapse supernova occurring. Now, it's a good thing that we do have supernova, because last time we spoke, I showed you that the human body was made up of about 50 odd different naturally occurring chemical elements, and most of these were produced in the core of a star. In fact, all of these were produced in the core of a star that exploded, and through all these materials seeded clouds of gas and dust, which collapsed down to form new stars and eventually new planets. So here we go. This is a picture of an area that is actually quite easily visible to us from the southern hemisphere, from a dark location. You see something called the Large Magellanic Cloud. It's a satellite galaxy of the Milky Way that lies about 168,000 light years away from us. And within it, we see this very large star-forming region here called the Tarantula Nebula. And back in 1987, we were privy to the eruption of a high-mass star. And there it is at the tip of the arrow, just right about here. So this is known as Supernova 1987A, or SN 1987A. So this marks the place where a star self-destructed. Now, the energy released by a supernova explosion is absolutely tremendous. In fact, the light and the energy released by a supernova explosion is staggering, to say the least. It's one of the biggest bangs since the big one, to quote from Douglas Adams, I must say. But nevertheless, when a supernova explosion occurs, the erupting star can outshine all the stars put together within that one particular galaxy. And it does so for a very, very brief period. So let's keep an eye out on that particular star. And this is what happened with Supernova 1987 erupting. As you can see, its magnitude, its luminosity grew millions of times of its original brightness. And this is what makes them easy to detect, especially whilst observing distant galaxies. So we can actually not see them. We've seen a few happening, but generally we see it after the fact. Now, moving on, This marks the place of supernova 1987A, and it's the energy released by a supernova is equal to the energy released by our sun over 9 billion years, except it gets released pretty much in an instant. Now, from the star erupting, or rather beginning in its dying phase, that can last for about 1 million years. The eruption, the core collapse, takes a quarter of a second, and then the explosion, the shock wave traveling through, takes a couple of hours, but then the light of it can fade off after a number of weeks. So I've got a picture here. Where is it? Oh, so this is a picture from supernova SN 2020 JFO. That happened last year while we were in lockdown over here in Western Australia, and I was doing my live sky astronomy broadcast, and this was quite fortuitous because I managed to capture this galaxy between the roofs of 2 houses, and I managed to document this. But this is a galaxy called Messier 61, lies about 40 million light years away, and what we'll do is we'll zoom up in a minute, but if you'll notice, there's a star right there that wasn't there a couple of weeks ago. So, or a couple of weeks ago when I took the image, I should say, I should clarify. But if we zoom up on it, what we see, that marks the place where a supernova occurred. So that is supernova SN 2020 JFO, and that occurred 40 million years ago, and we only just received the light back last year, which was pretty amazing, I must say. But supernova have occurred and has been documented by a number of ancient civilizations. The top picture here is a petroglyph from the Chacoan civilization in Chaco Canyon. And what we see here is the crescent moon. We see a hand, possibly that could be the signature of the artist, or it could be as a use to measure distances, like a marker or a ruler against the sky. And of course there's the erupting star there, and this does correlate with an eruption of a star, a known eruption of a star back in 1054, on the 4th of July 1054. And also Chinese astronomers documented the appearance of a guest star. So they also saw this during the day, or a guest sun, or the sun had a guest. So they also potentially saw this during the day as well, because it was that bright. So this formed the famous Crab Nebula, or the Crab supernova remnant, which is this picture here. This is where a reasonably advanced point of where a star exploded, and you can see this through amateur telescopes. But the next part of our talk will deal with what we can hear, or what we can detect with radio telescopes, and that's found deep within the heart, the remnants of a dead star. So of course we will now be talking about neutron stars and pulsars. Now, a friend of mine has just recently returned from studying at Cambridge University, and his main field of study is of neutron stars and pulsars. He's a radio astronomer, so he's finishing up, or he's doing his master's study in this field. So when a star of certain masses explodes, depending how much mass is left over from the resultant supernova, gravity collapses that mass down. Now, it can vary between, one solar mass up to about 2 or 3 times the mass of our sun. And the material that, the core that collapses down, goes to form a very, very dense ball about 20 kilometers across. Now, if we go back to how atoms are structured, where you have a proton at the center and an electron floating around in a cloud of probability around it, that is an atom. That is, I've just described a basic hydrogen atom. However, the pressures are so intense that the proton and the neutron are literally squeezed together to form a neutron. Now, the gravitational intensity of a neutron star is incredibly, incredibly intense, and I'll describe more about it just as we go on. But a neutron star is a very, very dense ball of a dead star. That's pretty much the best way to describe it. Now, we look here, we have huge magnetic fields that surround it. We have radiation beams that come out from the points of the magnetic axis, but then we also have a rotational axis. So like planet Earth and like all the other planets, it rotates on a rotational axis, but these jets of electromagnetic radiation get focused and go spewing out in opposite directions. And they can spin. They can spin at quite high velocities. So to give you a sense of scale, it's about 20 kilometers across. This is the city of Vancouver. It is a very small but dense remnant of a star that's self-destructed. That is a neutron star. So the material, the gravity on the surface, like here on Earth, if you were to jump from a meter high off a thing, by the time you hit the ground, you're traveling at 9.8 meters per second. In fact, that's the gravitational constant here on Earth, is 9.8 meters per second. So on the surface of a neutron star, the gravity is so intense that if you jump from a meter, you are traveling in excess of a few million kilometers an hour. And even jumping off a 1 meter high step would cause some serious damage to your persons. So the gravitational intensity on the surface of a neutron star is extreme, to say the least. But the material, because it's so tightly packed, so densely packed within itself, it equates to, imagine if you could stand on the surface of a neutron star and have a teaspoon and pick up, say, something about the size of a sugar cube. A sugar cube's worth of neutron star material would essentially weigh, because of the material being packed into such a dense area, would weigh about the size of same as Mount Everest. So this is an incredibly dense object and spins incredibly fast. Now I've got some examples here of various neutron stars. So here we go. Oh, before I tell you that, I've got to tell you about how they were discovered. Of course. Now, the person who discovered this was a grad student. This was done in February 1968. Graduate student by the name of Jocelyn Bell. Now it's Jocelyn Bell Burnell. But Jocelyn Bell, she was a grad student in radio astronomy, and she was in charge of actually, looking after the telescope, the radio telescope that's behind her, and of course gathering the data and scanning the skies for anything interesting. But she noticed, quote, a bit of scruff, unquote, on the incoming data recorder. Now, her supervisor at the time, Anthony Hewish, and her, because it was a rhythmic pulse, it repeated sharp pulses every 1.3 seconds, they thought it might have been a signal from an alien civilization, which is why they call that particular signal LGM number 1. And of course, LGM stands for Little Green Men. Now, Jocelyn Bell got a little bit annoyed because she really desperately wanted to finish off her research and get her PhD, but now she found this signal from alien civilizations, it will actually take away from her completing her PhD. So she got rather annoyed, but then they started noticing other of these pulses coming from the dark depths of the cosmos. The other one was about 1.2 pulses per second. So now they've actually stumbled onto a phenomenon, a astrophysical phenomenon. And eventually they found out, this piqued the interest of a whole bunch of other radio astronomers, and eventually they nutted out that these were the positions of these neutron stars that were sending out these beams of energy. And of course, pulsar is a contraction from pulsating star, pulsar. So they discovered a new astrophysical phenomenon. So quite an amazing discovery. In fact, a lot of these discoveries just happen by accidents, but the results are absolutely wonderful. So Jocelyn Bell's LGM signal showed us that stars do collapse upon themselves, and they do produce these radio beams that can act like lighthouses as they swing their beams around. And if you have a radio detector or a detector that can detect that kind of radio, or that detect that kind of interference or that signal, you can then start to pick up the whispers of the universe. Now, that, let's turn that down. That is the noise of Pulsar PSR B0329 plus 54. And each knock you hear, each knock you heard, was one of those electromagnetic arms passing by planet Earth. And we hear that blip, blip, blip. Like I said, it's like the arms of a lighthouse, and you see that flash of light from the top of the lighthouse as it sweeps past you. That was the same. Here's another one. It's probably a little bit noisier, but be sure to be ready for this. This, I think, is the Crab Pulsar. So as we can hear there, it's far more rapid. Each pulse, it sounds like a Harley cruising on a highway. Each pulse is the star spinning around very, very, very fast. To contrast the first one, that was spinning relatively slow. This one here is spinning quite fast. The next one, I do warn you, is extremely loud and extremely annoying. It sounds like a mosquito. Now this is what's known as a millisecond pulsar. And this one here is spinning incredibly fast. And the reason why these stars don't fly apart is because gravity is binding them together. Normally something spinning this quick would just fly apart, but it doesn't because gravity is holding it all together. So here we go. So as we heard there, that was Pulsar B1937 plus 21. That was a millisecond pulsar. That was extremely fast, to say the least. Black holes. Let's talk about black holes. In fact, I'd rather not, but I'm sure if I don't, I'd get a tsunami of abusive texts or whatever saying, please talk about black holes. Now, black holes are an enigma, to say the least. So for what we know about black holes is, well, when a star of a mass goes supernova, and what remains after that, the core, if it's anything greater than 8 times the mass of our sun, the core collapses down beyond the 20-kilometer limit to form a neutron star, to form a ball probably about 5 kilometers across that still weighs 8 times or more the mass of our sun. Now this is a very, very, very dense region that causes the local fabric of space and time to essentially wrap around it and disappear. It changes the shape of space in such an intense way that it disappears from what we can see. Now, black holes are made up of your basic parts. You have your accretion disk, which is any material, gas, dust, stars, people, well, not people, anything that strays too close gets ripped apart by the tidal forces. The closer you get to it, the more the tidal forces increase. So this is the material as it spins around, it heats up and it starts to glow. And this shows us the place where black holes are located. Then, of course, we have the event horizon. The event horizon is the point of no return. It is like the edge of a waterfall. The moment you disappear over the edge of the waterfall, you are gone. It's as simple as that. This could be, say, the river leading to the edge of the waterfall before you fall into oblivion. So the event horizon is the point of no return, and from that point of no return, the gravitational forces are so extreme that not even light can escape the clutches of the singularity. And it's at that point, everything beyond is where everything we understand about physics just completely breaks down. Somewhere in there is the singularity. Now, like I said, we don't really know much about what goes on in the center, but everything that we know, general relativity from Einstein, just breaks down and gravity becomes infinite. Now, here's a couple of pictures of black holes. Now, one was made in Hollywood, one is an actual image, but both were used for creating scientific papers. The top one, you might, if you're a film buff, this was from the movie Interstellar, where they created, using CGI, what they think a black hole would look like. Now, this is based, this work, one of the actual scientific advisor on it is a fellow called Kip Thorne. Now, Kip Thorne is the definitive expert on black holes and space-time. He's the head of the gravitational wave research across the world, and he was the scientific advisor for black holes and interstellar travel, and for the movie Interstellar, rather. And the actual model, the simulation that they used in the movie, was actually used to produce a number of scientific papers. Because what we're seeing here is we're seeing, of course, the black hole itself. We see the event horizon there, and we see the foreground of the disk extending along here. But because the black hole distorts space and time so much, this light, this hoop over here, is the back part of the black hole, or the accretion disk, that we cannot see because this gets in the way, but it has warped space-time so much we can see the back end of it. So imagine if you got your mate you're standing right on the edge here, and your mate walked all the way around and disappeared about there, but then you sort of start to see them sort of change shape and go a little bit weird, and then you sort of start to see them walking up there, and you go, for heaven's sake, what are you doing up there? And they're going, well, what are you doing up there? Because their view of you would be the same. But you'd think that they've walked not behind, but on top of the black hole, but they actually have walked behind. It's just space and time are distorted so much that you can actually see behind the black hole, and they'd be sitting right about there. So this is a model, you could say a computer model, but this thing is the actual image they've taken. So this is the real thing. It's pretty darned amazing. And this was only done a couple of years ago. This is the leading edge of the accretion disk. There's the black hole itself, and that is that back part right about there. So we have imaged a black hole for the very, very, very first time. So in fact, I think the first black hole to be discovered was Cygnus X1 in the constellation of Cygnus, the Swan. Now, this whole thing about light being escaped, or not being able to escape because the gravity is so strong, it depends how far away you are. So if you've got a light bulb out here, light can escape out, and light can be captured by the black hole itself. The closer you travel, the more and more light is captured, and the more light that can actually fall along the event horizon. But if you are right along the event horizon, the light would curl back upon itself and disappear. That is how extreme the distortion of space-time is. Now, I'll keep talking about space-time. It's this merging. This is Albert Einstein in his 1915 publication, The General Theory of Relativity, which describes how mass changes the shape of space, which is 3 spatial dimensions, forwards, back, side, side, up, down, and 1 dimension of time that's all interwoven to form this fabric called space-time. With the presence of matter, you can change, warp, twist, stretch, compress space-time. Now, with a massive object that is very, very compact, you can change the shape of space to such an extreme that light cannot move out of that distortion and gets trapped in there forever. So this is why we tend to lose light towards the event horizon, is because it just cannot escape. It just cannot get out of the gravitational clutches of said black hole. However, if you were to sit back and watch, say, again, get your mate to do this and not you, getting closer and closer and closer to the black hole, it starts to stretch out time as well. So if they could stand right at the event horizon of a black hole and then suddenly jump in, for them, that would be instant. They would jump in and they would disappear by the event horizon, and that would be it. But for you, because the light and space-time has been stretched so much, you'd see them as they jumped in, just to be sort of hovering there, and you're thinking, for heaven's sake, what are you doing? And then eventually, after a long, long period of time, they would fade off and disappear. But so what you're actually seeing is a light echo of what originally they were. But if they had a big clock strapped to their back, the closer and closer and closer they got to the black hole, you'd notice the clock on their back ticking slower and slower and slower and slower. That is because of the extreme changes in space-time around them. When I say space-time, not only does it stretch space, but it also stretches time out as well. And time is relative to where you are and how fast you are moving within a gravitational well or wherever. I'm probably not explaining this too well. I'm probably giving you more questions than answers, but this is the tricky thing about understanding gravity. It's more than just falling apples and hitting people on the head. Well, it didn't actually happen that way for Isaac Newton, but nevertheless, Einstein's picture of gravity is far more accurate and more elegant than Newton's description of gravity. So, one of the most extreme places in the universe are certainly black holes. Now, getting back to your old mate, getting too close to a black hole, they would experience something called spaghettification, as we can see by this poor fellow here, or lady, getting too close to a black hole. They would literally be stretched out. The gravitation or the tidal forces standing at the edge of the event horizon would be so extreme from the tips of your toes to the tip of your head that you will literally be pulled apart atom by atom by atom and spaghettified. And I'm sure it would hurt. So I don't recommend trying this, but nevertheless, this is the fate for not just wayward astronauts, but for stars and other bits and pieces that disappear beyond the event horizon. And yes, black holes do increase in mass when they have more material thrown in them. However, black holes, as Stephen Hawking put, black holes ain't so black, because they do evaporate from something called Hawking radiation. Hawking radiation is the creation of virtual particles at the event horizon where one can escape and one doesn't escape. Beyond that, I'm not a full bottle on it, but nevertheless, black holes do evaporate. And towards the end of the far, far distance of the universe, when all stellar production is finished, when all high mass stars have long gone, when even all low mass stars have long gone and all the red dwarf stars have cooled down, all that'll be left are black dwarf stellar remnants and black holes, and eventually the black holes will evaporate and disperse into individual photons. But for that time span is so mind-bogglingly huge. We're talking somewhere in the order of 10,000, here we go, 10,000 trillion, 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 trillion years into the future. It's staggering to even comprehend, saying, I mean, even just comprehending 13.798 billion years from the time of the Big Bang till now is still, it'll hurt your brain. But to comprehend how much time the universe has to go before it has stretched out and cooled and essentially there is nothing left is even further into the future. So with that, I will conclude this talk, and I'm hoping to come back eventually and join you another time, which will be fantastic. I'll just get rid of this screen here. Nope, that's not it. Nope, that's not it. That's the one. There we are. So I'm hoping to join you once again, maybe next National Science Week 2022. That'll be good. And give you another talk, but we'll see from there. But thank you very much once again. If you do have any questions, please put them in the comment section of the YouTube channel and I will endeavor to answer them. But apart from that, thank you very much once again, and hope you enjoyed the rest of National Science Week. So until then, thank you and goodbye.